Hi, so this video, or these next few videos, are going to be about the golden ratio. So I guess I should say, this video is about the golden ratio, which some people believe, that there's mysticism surrounding this, that it's some sort of important mystical number, some sort of key to the universe or something. And, well, I think there's many rational explanations as to why it seems to appear everywhere. I'm not here to debate whether there's, any sort of spiritual property to this thing or not. I'm here to talk about the mathematics behind the golden ratio. And specifically, I sort of want to offer a cute kind of argument that gives an explanation for why we might actually expect, from a mathematical perspective, to find the golden ratio so commonly in nature, as is claimed. So, okay, reminder for those of you who forgot, or those of you who don't know, I think the ancient Greeks were the first to really focus on the golden ratio. They basically said, imagine I had a line segment, and, okay, my drawing is not perfect, but imagine this is a straight line, and I have 2 points A and B. And they said, wouldn't it be nice if I could find some special point C such that when I take the distance from A to B, so I'm going to call that AB bar, so that's just the distance from here along this line to here, and I divide it by the distance from A to C, so I'm just going to write that as AC bar, then wouldn't it be nice if I just happened to pick C in such a perfect way that whatever this number is, it would be the exact same as picking the number AC with a bar here and dividing it by the length from C to B, which I'm going to write BC bar. And it turns out that we can always find such a C, and that these ratios, these divisions of lengths here, are always going to be the same number if we pick C in such this way. And it's normally written with a phi, and this is what's called the golden ratio. So the closed form formula of the golden ratio, the sort of the nice way to write it, is that phi is equal to 1 plus the square root of 5 divided by 2. Now it turns out this is an irrational number. So what does that mean? That means we can't express it just as a nice fraction of integers. There has to be something like a weird square root in here for us to write it down properly. Another way to express that idea is that in its decimal expansion, which goes something like 1.61803398875, and it keeps going forever, and there's no discernible pattern. It doesn't repeat after any point. It just keeps going in a seemingly random succession of digits. So that's what it means to be irrational, right? So this is the golden ratio. Okay, well, there's another important player in this story that you may have heard of before, and these are called the Fibonacci numbers. So Fibonacci, also known as Leonardo da Pisa, he was a mathematician in the 1400s, and so he came up with this sequence, and we're going to see that it has a relationship to the golden ratio, and that's sort of going to be the relationship that happens between the sequence and the golden ratio is sort of going to be our clue as to a mathematical reason why we might expect it to appear in nature so often. So the Fibonacci sequence starts off with the numbers 1 and 1. Some people started off with 0, but doesn't really matter. So it starts with the numbers 1 and 1, and how you get the next number in the sequence is you add the last two numbers. So 1 plus 1 is equal to 2, so that's our next number. And we need to find the next number in the sequence, so then we add the last two. So that would be 1 and 2, and so that would give us, of course, 3. And then we sum the last two numbers to get the next one. So 2 plus 3 is 5. 3 plus 5 is 13. 8. Math is all about making mistakes. 5 plus 8 is 13. 13 plus 8 is 21. 13 and 21 is 34. And we keep going like this forever. Okay. So, these are the Fibonacci numbers. Well, what did these have to do with the golden ratio? Well, it turns out, let's just introduce a little bit of notation here first. So this is I'm going to call this the 0th Fibonacci number, or another way I'll write it is f of 0, right? So that will be 1 here. Then this 1 will be f of 1. This 2 will be f2. This 3 will be f3. 5 will be f4, right? So what's happening here is I'm just making this, this is just to give us a set of labels by which to describe the Fibonacci numbers, right? So 1 is the 0th Fibonacci number, 1 is the first Fibonacci number, 2 is the second, 3 is the third, 5 is the fourth, 8 is the fifth, 13 is the sixth, and so on and so forth. Okay, so one thing we notice is that if we look at fn plus 1, so n is just some number, and we divide this by fn. So all this means is I take one of these Fibonacci numbers and I divide it by the number that came before it. Then this number should be, so the curly equal signs means approximately, so kind of close to. This should actually be approximately the golden ratio. Now, if we try this for the first couple Fibonacci numbers, this doesn't seem to really hold up. So if I go, right, 1 divided by 1, that's the first two Fibonacci numbers, that's 1. Well, okay, that's kind of close, but I don't know, off by more than a half, that's really not great. Okay, so let's go a little bit higher. So if we try 2 divided by 1, that gives us 2. Okay, that's a little bit closer. We were off by about 0.6 before, now we're only off by about 0.4. So let's try 3 divided by 2. Well, that's 1.5. Okay, that's getting us a lot closer, only off by 0.1 now. And we could try higher and higher ones, say, you know, if I skip a bunch and let's do 21 over 13, that gives us 1.61538. And I could keep going, let's say it went even further, and if I looked at, say, the 27th Fibonacci number divided by the 26th Fibonacci number. This is what, 31781 divided by 96418, right? And so if you go, you take the time to calculate all of these, we get a much better approximation. It's I think 1.61803339, right? So that's really close. We have the first few digits here bang on. So that's going to be it for this video, but I will continue the rest of the story in part 2.